Help if I unmuted myself. How's it going, folks or folk? I don't know how many people are here. Bring back memories, right? Memories of that first lockdown. Remember that first lockdown? Cool. So, for those people who can't tune in right now, obviously you're getting it on the rerun, so that's fine. How's it going, the rubber duck, whoever you may be? So I've not really got much of a plan for this other than just to sort of like, go through binary again. Obviously, I'll be able to go through it a lot quicker this time because you already know it. If you don't know it, then shout up so that I can recap stuff. But rather than me saying, hey, here's how you do this, now go and do a massive worksheet, it's going to be a case of me saying, hey, here's how you do this, try it out a couple of times, here's how you do the next thing, try that out a couple of times, and then you can go back and you can reattempt those worksheets and stuff from before. Does that sound good? Does that sound good? Just to let you know, I've got the Discord open. I'm sort of switching between the YouTube chat and Discord just to see who's on there. I can see there's a reasonable amount of latency. I've set this to super low latency, ultra low latency settings. Now you guys know what that means now, right? It still means that there's about a 5-second delay between what I say and what you see. But hey ho. So binary. We will go through. The first thing is the simple thing of converting binary to denary. Here's this awful joke which you've heard a million times, and it's just not as good as it as people make out. There is a better joke, by the way. There are 101 types of people in the world: those who understand even bit parity checking, and those that don't. But we'll get on to that. Here's an ancient meme. Remember that? Do you remember that meme? Yeah, from 2006 or something. Yeah. Smith wheeling out all the up-to-date hilarity here. So, we are going to have a look to start off with the difference between binary and denary, which you already know. So I'll just recap that briefly in case you are ever asked to explain what it means. We'll explain why binary is important in computing, and we will convert binary numbers to denary. We'll probably also have some time to do going back the other way as well. Okay, so binary is a way of expressing number values. It uses only 2 digits. It uses zeros and it uses ones. Now, inside the computer doesn't read zeros and ones. It reads voltages, right? It reads up and down volt. I've got a bit of a graph on the next slide to show you that. Okay, but ones and zeros. You can represent any value with ones and zeros in the same way that you can represent any value with the digits from 0 to 9. You can represent any value with just 0, 1, and 2 and stuff like that. You can, in theory, represent any value with a number of different symbols which are not actually digits, as long as you understand how they're going together. It is the only language a computer understands, which is why it is so important in computing. Computers inside have billions of tiny switches. If you can remember what those little tiny switches are called, just type it into the chat right now. I'm going to carry on talking regardless, but you can type that in there. Those billions of tiny little switches can either be on or off. Yes, you're absolutely right, Ollie. Transistors, those little switches are called transistors. They can either be on or off. And so if it is on, we treat that as a 1. If it is off, we treat it as a 0, and hence binary. So we're interested at the moment in looking at what the different values in binary represent and how to convert between them. Later on, we'll look at some more interesting stuff like how binary can be used to represent text and how it can be used to store sound files. So this is kind of what it looks like. Again, this isn't entirely accurate. We've got some a positive voltage up here and a negative voltage down here. You can see here it sort of like wavers around. It's not a set thing, sort of like, oh, here's the exact amount of voltage and then instantly down to the next amount of voltage and so on and so forth. It kind of like, it wavers around, but as long as it's above the 0, that still counts. So here, every time that voltage crosses the baseline, we're looking at potential changes there. Okay, so you don't need to know all of this stuff. I just thought it was an interesting thing to show you. So 1s and 0s, they equate to voltages being passed around inside your CPU. And when we get onto the CPU architecture section, we'll have a look at how they're arranged in logic gates. Okay, each digit in a binary number is called a bit. 8 bits make a byte. 4 bits make a nibble. Right, that you need to know those words. That's why it's very important when you're explaining things in like essay questions and stuff like that. Try and avoid using the word bit unless you're specifically talking about binary digits. Right? If you ever have a question which is to define what the word bit means, make sure that you don't just say, "Oh, it's a single binary number." Because it's not a binary number, it's a binary digit. This whole thing here, 01101010, that's a binary number. It's made up of binary digits, which are bits. Okay, so a bit is a single digit in binary. I'm just going to turn my light on. Okay, a bit is a single digit in binary. Right? 8 bits make a byte. You will be dealing with bytes most of the time. All right. But when we look at hexadecimal, then you'll be using nibbles to do the individual digits. All still on board, yeah? So this might seem basic, but I'm just going to recap it anyway. Right, the way that we write down our own numbers, like the normal number Denary counting system that you all are familiar with, right? We have these columns: hundreds, tens, and units, right? Ollie just asked a question. If I just quickly go back here, the little dips. It's not possible to have a sort of solid voltage due to the way that like the power is produced. So these dips represent where the voltage has been sort of like sent back up instead of being allowed to go back down. It's all voltage regulation is it's analog to digital conversion. Basically, there's always a little bit of noise in there. Is the simple answer. I know to those of you that know how exactly what's going on there. Obviously, there's a little bit more to it than that, but still. Right. So we've got our hundreds, tens, and units columns here. The number 375 is made up of 3 hundreds, 7 tens, and 5 units. Okay, this is all straightforward stuff. But if we were to write those values out as powers of 10, units, that's ones, right? 10 raised to the power of 0 is 1. 10 raised to the power of 1 is 10. And 10 raised to the power of 2 is 100. If we had the next column along, it would be thousands, right? That's 10 raised to the power of 3. The next column along would be tens of thousands. That's 10 raised to the power of 4. Okay, so we start off from 0 on the right-hand side and keep on raising the power by 1 each time. What that has the effect of here is multiplying by 10 each time. Okay, 10 raised to the power of 0 is 1. Multiply that by 10 and we get 10. Multiply 10 by 10 and we get 100. Multiply 100 by 10 and we get 1,000, and so on and so forth. Okay, this 10 here is known as the number base. Okay, Denary is a base 10 numbering system, which means that for each column of numbers that we have, each column of digits, we use 10 as the base number, which is raised to an exponential based on what column we are in. Okay, why am I telling you about Denary numbers like this? Because binary numbers are exactly the same, but instead of using powers of 10, we use powers of 2. Same structure here, right? 2 raised to the power of 0, 2 raised to the power of 1, 2 raised to the power of 2, 2 raised to the power of 3. The next one would be 2 raised to the power of 4, and so on and so forth. Because 2 is the base, we do not multiply by 10 each time we add a new column on. We multiply by 2. So 2 raised to the power of 0 is 1. 2 raised to the power of 2 raised to the power of 1 is 2. That's 1 times 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. 64 times 2 is 128. 128 times 2 is 256. 256 times 2 is 512. 512 times 2 is 1024. 1024 times 2 is 2048. 2048 times 2 is 4096. 4096 times 2 is 8192. 8192 times 2 is 16,384. 16,384 times 2 is 32,768. 32,768 times 2 is 65,536. Okay, it keeps going on and on and on and on and on and on and on. But because you are mostly dealing with bytes, you only need to know 8 of these. 1, 2, 4, 8, 16, 32, 64, 128. Okay, that will be the limit at GCSE level that you need to cover. Okay, if I just quickly go back to the previous slide here, underneath each of these numbers, that tells us how many of these things there are. There are 3 times 10 squared, right? 3 times 100, plus 7 times 10, plus 5 times 1. It is exactly the same here. But in binary, because we only have 2 digits, 0 and 1, it makes it a lot easier. It's still this number down here multiplied by the value at the top of the column, you know, the place number, these magic numbers at the top here. 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1 will give us the total value of this number. Okay, so because there is a 1 down here, that means there is an 8 in our total value. There is a 0 down here, which means there are no 4s in our total value. There's a 1 down here, which means that there is a 2 in our total value. There's a 1 down here, which means there is a 1 in our total value. So if we do 8 plus 2 plus 1, it gives us the total of 11, which is what this number in binary represents. Okay, I'm going to walk through that. But before I do, counting to 20, you know how to count to 20, right? And you probably know where I'm going with this. In computer science, we always start counting from 0, unless we're using a terrible programming language like Visual Basic, which I think the numbers it's arrays from 1, but you know, what can you really do? We're going to start counting from 0. If we count up, this is just Denary. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, an interesting thing happens when we shift from 9 to 10, right? There is no digit 10. We've reached the upper limit of the digits that we have, right? So if I add 1 onto this 9 here, what happens is we can't fill any more into this column. So this digit resets back to 0 and we add 1 onto the next column along. Okay, that's what happens when you count up past that threshold. 9 plus 1, you can't go above 9, so this resets to 0 and this gets 1 added to it, so it becomes 1, 0, which we know as 10. And we keep on going. 10 plus 1 is 11, 12, 13, 14, 15, 16, 17, 18, 19. The same thing happens here. We can't go higher than 9. So what happens is this column gets reset to 0 and that number, that 1, is added on to this column here to give us 20 or 20. Okay, does that make sense? I hope it makes sense, because that's sort of like, you should have learned that when you were pretty young. Right, so moving on. Looking at binary, exactly the same process happens there. When we reach the upper limit of the digits in a column, we reset to 0 and we spill over to the next column. But in binary, it's slightly different because we're not going all the way up to 9. We're only going up to 1 before we reset. So if I take this number 0000 That's obviously the value is 0. If I add 1 to that, then 0, 0, 0, 1. Straightforward, right? But now, if I add another 1 onto here, we can't go above 1. So when I add 1 onto this column here, what happens is this value resets to 0, and then the 1 is added onto the next column along. Okay? So 0, 0, 0, 1 plus 1 gives us 0, 0, 1, 0. Okay? We're now at the stage, where if we add another 1 here, because we're already on 0, we can do that. So we just add a 1 onto there. Okay? Hello, Tommy. How's it going? You missed the coffee ASMR. Okay? I add a 1 onto here, and we get 0, 0, 1, 1. Okay? The next thing, we're in a similar situation to if we had 99, for instance, and we were adding 1. Okay? We can't add 1 onto the 9 column. We can't add 1 onto the next 9 along. We have to spill all the way over, and it's the same thing here. We're adding 1 onto this column here. We can't do that. So what happens is we reset this number to 0, and instead we add the 1 onto this column here. But we can't do that either because we're already at maximum value here. So we reset that one to 0, and then we add the 1 onto this one. So if I start off with 0, 0, 1, 1, and I add 1 to that, we end up with 0, 1, 0, 0. Because this one got reset to 0, we then tried to add onto this one, that got reset to 0, and so we ended up adding onto this one. Does that make sense? There was coffee ASMR. It was over the top of some terrible music. I tried to play some chip tunes, and it was some medieval classical music played on an out of tune harp. So rock and roll there, rock and roll. But you'll be able to go back and rewatch it. Okay. If we carry on counting, we're going to add 1 to here, which means that 0 just becomes a 1. So we end up with 0, 1, 0, 1. And then if I add 1 onto this, this 1 is going to get reset. The 1 is going to spill over into this column, and we can add it on there. And so on and so forth. Okay. It's well worth your time just to practice that, adding 1 on, counting 1 by 1, incrementing these values all the way up to 15. Okay, so resets 8. We're going to add 1 on here. That's then going to reset, and we're going to add 1 on here. We can add the 1 on there. That's going to reset. That's going to reset. We add the 1 on here. That's where we end up. We now add the 1 there. That's going to reset, and we add the 1 on there. Add the 1 on there. And now, obviously, we've reached the maximum capacity for these 4 bits. If we wanted to add another 1 on there, obviously this one would reset, this one would reset, this one would reset, this one would reset, and we'd need another column here. Okay? C'est sensible? Wow. Sure, I set this to super low latency, but okay. Right. Well, going to move on. So, converting from... How do I get rid of this thing here? Hide the options menu. Why can't I hide the options menu? Oi, go away, options menu. There we go. If we are converting from binary to denary, it is super simple. Okay, you should by now understand the reasoning behind this, but even if you don't understand the reasoning behind it, you can still apply the method to convert this number. All you do is you look at the binary number, and any columns that have a 1 in the bottom, you are going to add the number at the top onto your running total. Okay, now I can't use my pointy thing because the menu keeps coming up annoyingly. So let's just go from the first column, 128. There's a 1 underneath that, so we're going to add 128 onto our running total. So at the moment I've got 128. There are no 64s in there because there's a 0 at the bottom, so we're not going to add 64 on. However, we are going to add 32. because there's a 1 underneath the 32. So we do 128 plus 32 to give us 160. Okay? There is a 1 under the 16. So we're now going to add 16 onto our running total. 160 plus 16 is 176. There's a 0 under the 8, so we're not going to bother with the 8. There's a 1 under the 4, so now we need to add that on. 176 plus 4 is 180. There's 0 under the 2, so we're going to skip over that. There's a 1 under the 1, so now we're going to add 1 on. So our total value is 181. So 10110101 when converted to denary is 181. Okay, and I think on the next slide, I've even got that written out. Oh, look, there we are. Okay, does that make sense? That's all right, Nick, don't worry. Tune in when you can. The whole thing will be up for the rerun. So I've just gone over some basic stuff so far. Okay. Okay, so that method, yeah? We got that method. You can convert any binary number to denary just by writing those numbers at the top. Now, when you write these, you don't always have to write out like this whole grid. Okay, obviously, you'll get to the point where you know what these numbers are. But I always find that it helps to... Yeah, the microphone's pretty good. It's a Tonor... can't remember the name of it. But yes, it's pretty good. It's a lot better than the potatoes at work, right? And I can do ASMR. Anyway. Oh, I just saw a spike in my viewers when I did that. So as long as you understand that the numbers start at 1 on the right hand side, yeah, and then they go up by 2 each time. 1, 2, 4, 8, 16, 32, 64, 128. Now at GCSE level, you won't need to go higher than 128. But if you did have a 9-bit number, then obviously you'd need another column, which would be 256. You know, if you had a 10-bit number, then you'd need another column, which is 512, and so on and so forth, okay? This method is the same regardless of the size of the number. If there's a 1 underneath it, you add your magic number on. If there's a 0 underneath it, you don't, okay? So for this number, 128, skip that, plus 32, plus 16, skip that, plus 4, skip that, plus 1, okay? That's it. That's all there is to it. Converting binary to denary, that's all there is. Okay? Good practice for this. Obviously, just coming up with random binary numbers and then converting them. You could write a Python program as well, which would go through that process. There's built-in functions in Python to convert things between binary and denary. But what you could do is... write a Python program to do that. Okay. That's that. There's another ancient meme. Remember these? Remember when that was all the rage? Probably not, because you guys probably weren't even born then. That's how old it is. Again, but now you can understand this terrible joke that everyone always repeats. And you know, this, whenever I get like birthday cards from people, they usually have like a joke like this on there, which is obviously super hilarious, and I've never heard it before. It's not a great joke, but at least now you'll be able to understand it. You know, obviously we're not talking about. Yeah, I know, what a sad life. I know. I'm still waiting for the day when someone gives me a card with a joke on it like, your mum is so fat the recursive algorithm calculating her mass generates a Stack Overflow. That would be a proper card. I got a Star Wars mug though one year for my birthday. Can't remember who gave me that. If only Star Wars was still good. But anyway, so that's the first bit of binary done and dusted. There we go. We've done a lesson already. Should we do the next bit of binary? Yeah. So that was binary to denary. Let's do denary to binary. And I need to sort out OBS because it's gone doolally. There we go. That's still... There we go. Okay, more binary. I know you guys love binary. Okay, so we've looked at converting binary to denary. We now need to look at how to do it the other way, denary to binary. It's exactly the same sort of concept. It's just going back in reverse. There's a couple of places that might trip you up. So here we go. Let's have a look. Just a quick recap from a whole 10 minutes ago or whatever long it was. What is a bit? What is a byte? What is a nibble? Can you sound off in the chat there? Just tell me what a bit, a byte, and a nibble is, in your own words. I mean, if you explain what a bit is, then you can explain what the others are in terms of that. A bit is one binary digit. Yes, excellent. Good. What's a byte? What's a nibble? And also, what's the highest number that can be represented with 4 bits? What's the highest number that can be represented with 8 bits? Why is the postman only now delivering mail? Back in a sec. What is this? Look, I've got a gift. Should we do an unboxing? So where are we? A byte is 8 digits. 256. What is the answer? What? Whoa. Let's be careful here. 256 is... Right, Ollie is on the case there. 1111 is the highest number that you can represent with 4 bits of binary, which is 15. Now, when you say 256, you are close. You're close to an answer, but there's a problem there. Remember, we start from 0. Although there are 256 different values that can be represented with 8 bits, the highest value is not 256. What is it? Oh, sweet! Look at that! Got my new book. My Tank is Fight. There we go. Yeah, it's 255. 255. Excellent. Look forward to reading that. Okay. Cool. So the easiest way of remembering how to work out the highest value that can be represented with a given number of bits is if you work out what the next magic number along would be, and then subtract 1 from it. So if I've got 4 bits, my magic numbers at the top are 1, 2, 4, and 8, starting from the right and heading to the left, right? The next magic number along would be 16. So subtract 1 from that, and I can see that 15 is the highest number that I can represent with 4 bits of binary. Okay? You joke about that, Tommy, but My Tank is Fight it came out. It was made by some guys on the Something Awful forums, which has a long history with the whole all your base thing. So yeah, the title was a kind of a joke, but yeah. Anyway. If I had 8 bits of binary, my numbers go 1, 2, 4, 8, 16, 32, 64, 128. The next number along would be 256. So subtract 1 from that, and the highest number that I can represent with those 8 bits is 255. Okay, does that make sense? Doesn't matter if it makes sense or not. I'm moving on. Cool, Ollie in there. I'm going to skip over this because this is something that you can do in your own time. But you might want to make a note of those numbers. In fact, I can type them into the chat now. 1011, 1101. I'm wondering if the latency is bad enough that these numbers are just appearing and you're thinking, what the hell's he typing? 111 000100101. So good practice. Don't do it now, but copy those numbers out and have a go at converting them. And if you drop me the answers on Discord, I can say yay or nay. So what we're going to do, as I promised you, is working out how to convert back from Denary to binary. Okay, so it's a little bit more tricky, but it's not really that bad. Okay. Now, what I've done in this example is I've said start off by working out how many bits will be needed to represent the number. But for GCSE, you are always going to use 8 bits, right? So you probably don't need to do this bit necessarily. However, here's a nice little table showing you the highest value representable by all of these different numbers of bits. So for this example, I said we're converting 73. So if I want to find out how many bits I need, well, I need more than 6 because the highest value I can represent with 6 bits is 63. And I don't need 8 bits because I can go all the way up to 127. So I know I need 7 bits for I need 7 bits for 73. If in any doubt, just go with 8 bits. I mean, you can use 8 bits to represent any number up to and including 255. You know, the number 1 in 8-bit binary is 00000001, for instance. Okay, so don't be afraid of using full 8 bits. But what we're going to do is, and as before, I said that you don't have to write these like columns out every time. As long as you know what the numbers represent, you should be all right. However, when you're sort of practicing, it helps to write out those magic numbers, right? In fact, I would recommend starting off with your, it's good sort of like habit to learn the numbers 1, 2, 4, 8, 16, 32, 64, 128. Okay, because we only need 7 bits to represent this number 73, in this example I haven't bothered with the 128 there because that would just be 0 anyway, right? But this is the way that we do it. You start from the left hand side. Oh, I've added the extra column on here for some reason. #consistency. You start from the left hand side and you check to see if the value in the column is less than or equal to the number that you're converting, right? So if the number that you are, if the value at the top of the column is less than or equal to the current number that you are looking at, you're going to put a 1 in the box and then subtract the value from the number you're converting. So for instance, 73, 128 is greater than 73. So we're going to put a 0 in the 128 box. Yeah, 64 is less than 73, so we're going to put a 1 in the 64 box and then subtract 64 from 73. Okay, once we've subtracted 64 from 73, the new value that we're looking at for the rest of the calculation is whatever that answer is. So 73 minus 64 gives us 9. So in the next column, the 32 column, we're comparing that with 9, not with 73 anymore. Okay, so 32 is greater than 9, so we're going to put a 0 in that column. 16 is greater than 9 as well, so we're going to put a 0 in that column. 8, on the other hand, is less than 9, so we're going to put a 1 in the 8 column. And then subtract 8 from 9, and that gives us 1, right? And so on and so forth. I think on the next slide I sort of explain this in some more detail. Okay, so in the 64 column, you can see because 64 is less than our original number 73, we're going to put a 1 underneath it, and then we subtract 64 from 73. Yeah, what I should probably do is have a whiteboard where I can show you this stuff. Give me a second and I'll sort that out, but I'll keep on soldiering forward. Hopefully this is making sense to everyone. Okay. Keep on, and we keep on going. Bear with me. Better than paint, I've got GIMP. Oh God, I don't want that red. Right, I've got a whiteboard of sorts. Let me just add that to OBS. Right. Let's just use this. He says, desperately tries. So, oh, I'm looking at the wrong thing, that's why. Right. Let's just use this as a quick example. So, for instance, the number that we were converting was 73. I don't have. I'm running Linux at home, so I don't have Paint. Sorry about that. You'll have to make do with something better. It would help if I actually had a color selected. There we go. So 73. Let's change the. Maybe that's too big. So 73 is the number that we're converting. We have all of those numbers written across the top. 128, 64, 32, 16, 8, 4, 2, 1. Okay? So the first thing that we do is we check this first number here. Right? If this number is less than or equal to this number, we put a 1 in the box here. If this number is greater than this number, we put a 0 in the box there. This number is greater than that number there, so we're going to put a 0 in the box there. Right? If we put a 0 in, we keep on going. Right? But now we've got 64. 64 is less than 63. 73. So we put a 1 in this box here. Okay, that's a 1. The next thing that we do is we subtract 64 from 73. So I've got 73 minus 64. What's 13 minus 4? 9. And there we go. The answer is 9. Okay, now this 9, that is now our new number that we are using to compare against these things here. 73, that's done now. Okay, we're past that. We're comparing 9 to these numbers here. Okay, so now we're looking at 32, comparing it with 9. 32 is greater than 9, right? So we're going to put a 0 in the box there. Okay, and we move along. 16 is also greater than 9, so we're going to put a 0 in the box there. Yeah, and we move along. 8 is less than 9. So we're going to put a 1 in our box there, and then we're going to subtract 8 from 9. Okay? 9 minus 8 is 1. That 1 now becomes our new value. So the 9 is done, yeah? And we're working with this 1 here. Comparing 1 with 4. 4 is greater than 1, so we're going to put a 0 in the box there. Moving along, 2 is greater than 1 as well, so we're going to put a 0 in the box there. 1 is equal to 1, so we're going to put a 1 in the box there, and just for completeness, what we would do is then subtract 1 from 1, and that equals 0. At the end of all of this, you should end up with a running total of 0. If you get to the end and you've put numbers, 1s and 0s, under each column and you're left with something other than 0 at the end, you've messed up somewhere. Okay? Does that make sense? Are we all good? Nick, is this making sense to you as well? Excelente. Okay, cool. So I'll keep GIMP there on hand, and I will. Yeah. No, no worries. You carry on Discord. That's fine. Right. Let's just move that GIMP out of the way. Okay. So we have done conversions from binary to Denary, and we have done conversions from Denary back to binary. Okay. And hopefully that all makes sense. There are worksheets for this, by the way, Nick, on Google Classroom. If you need to sort of just make sure that everything makes sense, then you can go back and do those worksheets on Google Classroom. They're probably buried all the way down the bottom. If you do them and you submit them, I'll mark them for you. All right. So that's Denary to binary and binary to Denary. Should we move on? We can move on, because we've also got binary addition. Okay. And what's going on here? Nope, did not mean to do that. Don't do that. Has that sorted? Oh, God's sake, OBS. Will you sort your life out? Where's the presentation thing? There we go. Okay. So binary addition, pretty straightforward stuff. I'm going to try and blast through this fairly rapidly. The important bit is understanding what overflow errors are, although technically they're not errors, they're just properties, but yeah. And we'll also look at binary shifts. Okay, so what time is it at the moment? 5 o'clock. I reckon we can get through this in about 15-20 minutes. What say you? So we're going to have a look at, we've been through this like literally 15 minutes ago, so not gonna bother with that. But again, some more practice, converting 147 to 8-bit binary, converting 110 11001 to Denary. Pretty straightforward. Again, really good practice for this, for making sure that you understand the process, is writing a Python program that does this conversion without using the built-in Python binary conversions. Okay, that's a little project there for you. Okay, so once again, going to take you back to the old school addition maths from your early years of learning. Adding in binary uses exactly the same principles as adding in Denary. They're literally the same. Okay, it just seems a little bit different because we're only dealing with 2 digits. Okay, so when we're adding in Denary, we have a column system like this, right? Well, we've got our hundreds, tens, and units. If I'm adding 147 plus 36, what I would do is write them out in a similar fashion to this, and then I'd start from the right-hand side, add up the units first. 7 plus 6 is 13. But I can't write 13 in that column, so what I do is I write 3 at the bottom, and then that 1 carries over into this column. Okay, I might blast up GIMP again, just so that we're on the same page with this. Give us a second. Boom, there we go. Let's delete all that. Oh no. How angry is that? Okay, so if I'm adding 2 numbers together, what did I have? 147? Was it 147? 147 plus 147 plus 36. Yeah. If I do 7 plus 6, I get 13. I can't just write 13 like that. That ain't going to work. I also can't find the eraser tool. There it is. Okay, so what I do instead... Oh, come on, man. Let's have a... So what I do instead is I write the... Oh, I see. The size of the brush is the same. So I write the 3 here, and then I will carry the 1 down there. Okay, and now that 1 gets added on to our running total in this column as well. 4 plus 3 is 7, plus that 1 is 8. So I can write the 8 in that column there. And then this 1, we're effectively, this gap is basically saying that's 0. So 1 plus 0 is 1. 147 plus 36 is 183, right? That should not be news to you, okay? But I wanted to go over it with you to remind you of why we do that, so that doing it in binary makes more sense. Okay, so there are only 5 rules that you need to know for binary addition. Okay, 0 plus 0 equals 0, fair enough. 1 plus 0 equals 1, that makes sense. 0 plus 1 equals 1, that makes sense. Now it gets a little bit more tricky down here. 1 plus 1 is 0 and carry the 1. Right, and 1 plus 1 plus 1 is 1 and carry the 1. And again, that makes sense when you think about it in similar terms to this, yeah? Because if I did 1 plus 1, that equals 2, right? 2 in binary is 1, 0, yeah? So if I'm doing 1 plus 1, yeah, I can't write 1, 0 down here. That ain't gonna work. What I have to do instead is I write the 0 in this column here. I write the 0 there, and I carry that 1. Just like here, where I had 7 plus 6 equals 13, I write the 3 there and I carry that 1. When I've got 1 plus 1 in binary, because we can't go up to 2, right? 2 in binary is 1, 0, so I write the 0 here and I carry that 1 down there. Likewise, if I had another 1 and a 1 here, if I'm adding this up, I have 1 plus 1 plus 1. Well, that's 3. 3 in binary is 1, 1. Okay, and so once again, I write the 1 here and I carry the 1 down there. And that's why 1 plus 1 is 0 and carry 1, and 1 plus 1 plus 1 is 1 and carry 1. Okay, hoping that makes sense to everyone. Right? So if we're adding this stuff together, ordinarily I'd write on the board with this, but I'll switch back to GIMP in a second. If I've got 1, 0, 1, 0 plus 0, 0, 1, 1. In fact, let's GIMP that up. Give me a second just to erase this nonsense. There we go. And go back to my paintbrush here and open up GIMP. So what have we got? We've got 1, 0, 1, 0 plus 0, 0, 1, 1. Okay, we're adding these together. 0 plus 1, that's easy. That's 1, just like in Denary. 1 plus 1 is 0 and carry the 1, because that would normally be 2. Okay, so 0, carry that 1 down there. Now we've got 0 plus 1, that becomes 1, and then 1 plus 0 is just 1. Right? We can prove that this is correct by doing a quick binary conversion on these numbers. Okay, 1, 0, 1, 0 is 8 plus 0 plus 2 plus 0. 8 plus 2 equals 10. I've just got another delivery through the door. Give us a second. Bye, mate. Yeah, nice one. Man, I'm getting so much stuff through the post. Unboxing. What is it? Oh, cool. Paints. Wicked. Anyway, so 8 plus 2 equals 10. And then down here we've got 0 plus 0 plus 2 plus 1. So 2 plus 1 equals 3. So in theory, we should be expecting this to be 13 because 10 plus 3 equals 13. So if we do 8 plus 4 is 12 plus 1 equals 13. We can see that that is correct. Okay? That, my friends, is all there is to binary addition. Now, obviously, I've shown you adding 2 nibbles together here, but it's exactly the same adding 2 bytes together. Okay? No, it's no different. When we run into problems when we end up with a sum total which is greater than the maximum value that can be stored with the number of bits that we have. Okay, that's the next thing that we're going to look at here. Not going to look at that. So if we have this, for example, yeah, we've got what have we got here? 11010011 plus 0110011. We're going to run into a spot of bother when we add this up. Okay, so let me just quickly draw this out in GIMP here. 11010011 and 01100110. And turn my GIMP back on. Boom. Okay. When we're adding this stuff together, we end up with 1 plus 0 is 1. 1 plus 1 is 0 and carry. 0 plus 1 is 0 and carry. 0 plus 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 0 and carry. And now we're in a situation where we need to add 1 and 1 together. And what happens is we can't carry that 1. There is no extra column. Now, if we were doing this on paper, the temptation would be to just say, 0, and then instead of carrying that 1 down there, we would just write it as a new column here. Okay, but computers can't do that. They can't dynamically allocate additional bits. Okay, we have a set amount of memory space allocated and we can't go over that. So what happens is the additional carry is just discarded. It's lost. It's gone. Right? And this can cause all manner of problems. It's what's known as an overflow. Okay? So an overflow is when the number that you need to store requires more bits than you have allocated for storage. It can cause all sorts of problems. Okay? So some useful stuff. The exam board loves asking you about overflow errors. It loves asking you, what it means and what problems they can cause. Right. So if we add 2 bytes together and they come to more than 255, we can't represent the answer with 8 bits. Okay. We'd need 9 bits to represent that. We can't just write the extra bit. We have a set amount of space allocated. Okay, so when the number that needs to be stored requires more bits than there are allocated for its storage, it's called an overflow. Yeah. I'm sure I told you this story before. This was the story of the Sword of Vermilion cheat, where you have a cursed weapon, and every time you remove the curse, your weapon gets removed, but you permanently lose a point of strength, right? And what happens is you start off with strength 10, you equip the cursed weapon, and then you have it removed, and your strength goes down to 9. So you equip it again, you have it removed again, your strength goes down to 8. You have it equipped again, and then you remove it. It goes down to 7, and then down to 6, down to 5, down to 4, down to 3, down to 2, down to 1, down to 0. And if you equip it again, because of the way that the numbers are stored, it doesn't go down to -1. It sort of resets itself to 65. No, it goes up to 255, not 65,536. That was the armor value. Okay, because what's actually happened is you've tried to go below 0, and it's had to reset it to the maximum value, which is 255. If anyone's played Civilization as well, that's the other example that I always use. Gandhi is the most likely to start a worldwide thermonuclear war because he starts off with a peace rating an aggression rating of 0, and if you give him a gift, giving people gifts reduces their aggression rating. And so if you start off with an aggression rating of 0 and you give him a gift, what happens is it goes below 0, and then it wraps round to a really high number, and then he just kicks off and starts throwing nukes all over the place. Okay, obviously these are just examples of the way that overflows can be bad in video games. But if we're talking about something in real life, like for example, something that is controlling a coolant system in a nuclear reactor, for instance. The core heats up, it keeps going. Maybe it gets hotter than 255 degrees. It goes up to 256 degrees, but we only have 8 bits allocated. We can't store that extra bit, right? If it goes up from 255, which is 1111111, and it goes up to 256, which would be 100000000, well, that extra 1 is discarded. So all the computer sees is 000000000, which is 0. So the computer says, wow, it was a bit hot. It was 255 degrees, but now it's fine. It's 0 degrees. I no longer need to engage my coolant system. Okay, and you can see where that goes. Hopefully that makes sense why overflow errors can be bad. Okay, just a couple more points to go over, and then we'll wind it up for today. Okay, and that is the concept of binary shifts. Okay, hopefully you're all still with me. I hope this is still making sense, and I hope this is valuable to you. So multiplying by 10. You all probably know the trick for multiplying by 10. You might think of it as just, you add a 0 on. If I multiply 145 by 10, stick a 0 on the end and it becomes 1,450. Right? If I multiply it by 100, I add 2 zeros onto the end of it. Okay? However, try not to think of it as adding zeros on the end. Try to think of it as shifting the decimal point along, or shifting the numbers forward and backward with the point fixed in place. So what I've actually done here, if you imagine 145 is the same as 145.0, and when I multiply by 10, what I actually do is shift all of those numbers to the left. Okay, I can again demonstrate this in GIMP for you. Let's just delete all this stuff. Goodbye. So if I have my, if I've got 145, looks more like a 6, so let's go with 146.0. I apologize for that number. It's the worst number anyone's ever. Oh my God, I've just made it worse. 146.0. If I want to multiply that by 10, what I'm essentially doing is taking each of these numbers and shifting them along one space to the left. Okay, that point stays where it is. Yeah, that 0 is being shifted along here. So our 1 ends up here, our 4 ends up here, our 6 ends up here, and our 0 ends up here, and that point is there. I've multiplied that by 10. Okay, because it's Denary, if you shift the spaces to the left or to the right, you are multiplying or dividing by 10, because Denary is base 10. Okay, what's binary? What is the number base of binary? Can someone tell me what the number base of binary is? Yeah, it's 2. So instead of multiplying by 10 each time when we shift, we're multiplying by 2 each time, or dividing by 2 depending on the direction. Okay, so I'm not going to go on about Denary. Let's look at binary. Here's a little table which seems a little bit more difficult to understand than it needs to be, but still, if we have these numbers here, 0 0 0 0 1 0 1 0, if I take all of these numbers and I shift them along one space to the left, what it actually does is it multiplies that whole number by 2. And it stands to reason, right? If I take this 1 and I move it along one space, it's now no longer telling me that there's an 8 in my number. It's telling me there's a 16 in my number. If I take this 2, this one here, move it across here, there's no longer a 2 in my number. There's a 4 in my number. Okay? So we can also calculate the total values here. 8 plus 2 is 10, and I've taken this whole lot and I've shifted it across. The zeros are sort of like, pulled in from the nothingness. I now, instead of having 8 plus 2, I have 16 plus 4, which is 20. 20 is 2 times 10, and so on and so forth. Okay, so every place that you shift to the left increases the it multiplies it by a factor of 2. But you've got to be careful, right? If I shift once, then it's times 2. If I shift twice, it's times 4. If I shift 3 times, it is not times 6, it's times 8, because you are doubling each time. Okay? So if we shift to the right, what happens is we divide rather than multiply, right? There is a neat little trick that you can do where you can work out what the relative values would be. If I just go back to my previous slide here, if I shift once to the left, if I start off on the far right hand side of my magic numbers here, and I count one space along, that's equivalent to a left shift once, where you can see it multiplies by 2. If I shift twice, I can hop 2 spaces along here, 1, 2, and I can see it multiplies by 4. If I shift it 5 times, for instance, 1, 2, 3, 4, 5, I can see that a left shift 5 spaces will multiply the number by 32. Okay, it's the same deal with division. Obviously, if you're shifting to the right, you are going to be dividing. If I shift to the right once, it's going to be divided by 2. If I shift to the right twice, it's going to be divided by 4. If I shift to the right 3 times, it's going to be divided by 8, and so on and so forth. Okay, now what happens if you have a 1 and that gets shifted off? It's just gone. It's lost. It's gone forever. Okay, it can't be brought back. It's similar to an overflow error. This is an underflow, if you like. Okay, so you lose some accuracy if you're shifting off the end, just as you would lose some accuracy if you were shifting off this end by multiplying. Okay, does that make sense to everyone? Now, in any exam, you will only ever be given nice numbers to multiply by. You'll have something like, multiply this number by 8 using binary shifts, and it's a case of, okay, cool, I just need to shift it to the left 3 spaces. Generally speaking, you'll get a mark for getting the direction correct. You'll get a mark for the number of spaces that you shift. Okay. So things to remember: shift left to multiply, shift right to divide. Okay, left multiply, right divide. Okay, one way to think about that, what happens when you shift the ones off the end, it's like you ditch the remainder. Like if I just go back to this example here, if I was dividing this number by 2, I've got 8 plus 2 plus 1 is 11. 11 divided by 2 is 5.5, or 5 remainder 1, right? If I were to shift that to the left one space, I end up with 4 plus 1, which is 5. So that 0.5, it goes away. We're sort of like ditching everything after that decimal point. Okay? Hopefully that makes sense to everybody. And that's really all we've got time for tonight. Okay, so there are multiple worksheets on the classroom. Obviously, if you've done them before already, you can go back and you can sort of like practice those. Yeah, we're finishing up now. This is the end. Okay, so you can go back and you can review that whenever you want. Ask me any questions that you might have. And next time we will look at some more advanced binary stuff. We'll look at hexadecimal and stuff like that. Probably on Tuesday. I think Tuesday is the next best time to do it. All right. Thanks very much for your time, everybody. And I will see you when I see you. No, you don't have to know how to multiply by odd numbers.